Lecture 7.5, Part 1, Work and Pumping Liquids. This is Hoover Dam on the Colorado River between Nevada and Arizona. This is the powerhouse for Hoover Dam. And to give you a sense of scale, there's a man on a golf cart right there. It's a pretty big place. First, a review. Hooke's law. F equals kx. A spring has a natural length of 1 meter. A force of 24 newtons stretches the spring to 1.8 meters. Find K. We have F equals kx. So 24 equals K times 0.8. Dividing by 0.8, we get 30 equals K. So our force equation is F equals 30x. How much work would be needed to stretch the spring 3 meters beyond its natural length? Work would be the integral from a to b of f of x dx. That's force times distance. So in this case, it's the integral from 0 to 3 of 30x dx, or 15x squared, evaluated from 0 to 3, which gives us 135 Newton meters. Over a very short distance, even a non-constant force doesn't change much, so work becomes f of x dx. If we add up all these small bits of work, we get work equals the integral from a to b of f of x dx. Example: a leaky 5-pound bucket is raised 20 feet. The rope weighs 0.08 pounds per foot. The bucket starts with 2 gallons, or about 16 pounds, of water, and is empty when it just reaches the top. We want to calculate the work. We set our scale with 0 at the bottom and 20 at the top. So for the bucket, the force is constant. Work is force times distance, so we have 5 pounds times 20 feet, or 100 foot-pounds. For the water, the force is changing as the water leaves the bucket. The force is proportional to the remaining rope. So the force would be f of x equals 20 minus x over 20 times 16. 20 minus x over 20 gives you the fraction of the rope that's left. We can simplify, and we get 16 minus 4/5 x. Just a quick check to make sure we've got it set up correctly. At x equals 0, the force is 16, that is the entire weight of the water. By the time x is 20, the force would be 0. Work equals the integral from a to b of f of x dx, or the integral from 0 to 20 of 16 minus 4/5 x dx. Taking the antiderivative, we get work equals 16x minus 2/5 x squared, evaluated from 0 to 20. We plug in the 20, and we get 160 foot-pounds. Now for the rope. Force of the rope is not constant either. We have f of x equals 20 minus x times 0.08. 20 minus x would give us the length of the remaining rope, and 0.08 gives us the weight per foot. Quick check here. At x equals 0, the force is 1.6 pounds, which is the entire weight of the rope. At x equals 20, the force would be 0. So work is the integral from 0 to 20 of 1.6 minus 0.08x dx, which is 1.6x minus 0.04x squared from 0 to 20. Plugging in the 20, we get 16 foot-pounds. So the total is 100 plus 160 plus 16, or 276 foot-pounds. Here's another problem. I want to pump the water out of this tank. How much work is done? Work is force times distance, and we'll set up our scale with 0 at the top and 10 at the bottom. The force is the weight of the water. The water at the bottom of the tank must be moved further than the water at the top. Now that might seem counterintuitive, but we know that water tends to search for its own level, so the water at the top could move down and back up without using any extra outside force. So we only have to be concerned with the distance the water moves from its original position up to the top of the pipe. Consider the work to move one slab or slice of water. The weight of the slab equals the density times the volume, or 62.5 times pi times 5 squared dx, which is 1562.5 pi dx. The distance it has to move is x plus 4. We have the distance from x plus 4. We have the distance from 0 to the slab, which is x, and 4 additional feet to the outlet. So work equals x plus 4 times 1562.5 pi dx, where we have distance and force. Our integral then becomes the integral from 0 to 10 of x plus 4 times 1562.5 pi dx. We can move the constant out front and then find the antiderivative. Plug in the 10. And we get the work is approximately 441,786 foot-pounds, which is, of course, too many significant digits. A 1 horsepower pump rated at 550 foot-pounds per second could empty the tank in just under 14 minutes. A conical tank is filled to within 2 feet of the top with corn oil, weighing 57 pounds per cubic foot. How much work is required to pump the oil to the rim? Say we drop a hose down to the bottom. We have to pump the oil out. Consider one slice or slab first. Work equals force times distance. Which is density times volume times distance. The density is 57 pounds per cubic foot. Now we set our axes in, and we notice that this point here would be at x equals 5, y equals 10. So we could write the equation of this line. It's y equals 2x because the slope is 2 and it goes through the origin. If y equals 2x, then x equals 1/2 y. And x is the radius of the slice. So the volume is pi times 1/2 y quantity squared times the thickness, which is dy. The distance then that the slice has to move is 10 minus y. Our integral becomes the integral from 0 to 8. We go from 0 to 8, not 0 to 10, because the last 2 feet don't have any oil. So we have the integral from 0 to 8, 10 minus y times 57 pi times 1/4 y squared dy. We move the constants out front. Then we find the antiderivatives. Plugging in the limits of integration, this simplifies to approximately 30,561 foot-pounds.